everyone, and welcome. Today, we're diving into a classic engineering dilemma. When is just following the rules not actually good enough? We're going to start with what seems like a simple question about a huge electrical switch, but trust me, it uncovers a really critical lesson about why the easy way out can be secretly dangerous. So this is the question that kicked everything off, from an engineer we'll call Binwork 91. Here's the setup. They've got this massive 4,000 amp main switch, and it's already protected. But further down the line, there's another pretty big 1,200 amp switch. The heart of the problem is, does that second switch need its own protection too? And the answer? Well, it could be the difference between a tiny little hiccup and a catastrophic full facility blackout. To get the official answer, there's only one place to look: the rule book. For electricians and engineers in the US, that's the National Electrical Code, or the NEC. It's basically the Bible for safe electrical work. So let's see what the code has to say. Okay, time to put on our detective hats and dig into the specific rule that applies here. First off, let's just quickly define what we're talking about. Ground fault protection, or GFP. You can think of it like a super smart emergency brake for a big electrical system. If electricity ever starts to leak where it's not supposed to, that's a ground fault. GFP slams on the brakes and trips the breaker, preventing things like fires or equipment meltdowns. It's a big deal. And this brings us right to the rule in question, NEC 215.10. It says, and I'm paraphrasing a little, that any big feeder disconnect that's 1,000 amps or more on the kind of high voltage system we're talking about shall, that's the keyword, shall be provided with ground fault protection. Since our engineer's switch is 1,200 amps, this seems like a pretty open and shut case. Yes, it needs it. Let's just quickly run through the checklist to be sure. Is the disconnect 1,000 amps or more? Yep, it's 1,200. Check. Is it a solidly grounded Y system at 480 volts? Yep. That's a super common setup for commercial buildings, and it fits the scenario perfectly. So based on the main rule, that second switch absolutely 100% needs protection. But as anyone who's ever read a legal document knows, the real story is often hiding in the fine print. And in the NEC, that means looking for the exceptions. And there it is, exception number 2. It says that the whole rule we just read doesn't apply if protection is already provided on the supply side, which is just a fancy way of saying upstream from the switch we're looking at. And since our engineer's main 4,000 amp switch already has that protection, well, this exception changes everything. So there we have it. The official, technically correct, by-the-book answer is no. The code does not legally require that second 1,200 amp switch to have its own protection. Okay, so case closed, right? The engineer can skip the extra cost and move on. Problem solved. Well, not so fast. This is where the simple answer gets really, really complicated. And this is the moment we have to shift from thinking like a lawyer to thinking like an engineer. It's the classic showdown, what's legally required versus what's actually desirable. This comment from a retired state electrical inspector, Augie47, just hits the nail on the head. He confirms, yep, it's not required. But then he drops this critical term, selective coordination. And honestly, this concept changes the entire game. So what in the world is selective coordination? I promise you, you already know the concept. Think about the breaker box in your house. If your toaster goes haywire and shorts out, the breaker for your kitchen trips, right? But the lights in your bedroom and the TV in the living room stay on. That is selective coordination. It isolates the problem to the smallest possible area without taking the whole house down with it. This chart really lays out the two choices. On the left, you have the code minimum approach. You've got one giant protector for the whole system. It's cheaper, sure, but the result is that any tiny little fault, anywhere, causes a total system blackout. On the right, you have the best practice, selective coordination. You have multiple layers of protection. A small fault only shuts down its own little zone, the rest of the building stays up and running. It is literally the difference between using a scalpel and a sledgehammer. And we're not just talking about theory here. Choosing that code minimum sledgehammer approach has some very real and often very, very expensive consequences. Another expert, an electrician and inspector named Texie, puts it about as bluntly as you can. He says that taking the cheap code minimum route almost always ends with a very unhappy customer down the road. Why? Because the cost of just one total system blackout in lost productivity, lost data, maybe ruined manufacturing product can completely dwarf whatever money was saved up front. Let's just walk through exactly what happens. Picture it. A small, minor ground fault happens in one piece of equipment way down on that 1200 amp circuit. But because there's no local protection, that fault signal travels all the way back up the line until it hits the main 4000 amp breaker. And that giant switch does its job and trips. And just like that, the entire facility goes dark. Every office, every machine, every light, gone, all from one tiny, localized problem. And that brings us to the most important takeaway of this whole thing. Following the electrical code is not the same as following best practices. The code isn't a guide to designing a great system. It's the absolute bare minimum you have to do to be safe and legal. It's the floor, not the ceiling. A great engineer doesn't just ask, does this meet code? They ask, does this make for a robust, reliable, and resilient system? So we come full circle. The initial question was, do I have to add this protection? But we've learned that's the wrong question. The real question is, can my client afford for me not to? Is that small amount of money saved up front really worth the massive risk of a catastrophic facility-wide blackout later? And when you put it that way, the answer is pretty clear, isn't it?